Hey there, Braille students. This week we're going to be adding on to the other types of equations you already know how to write. You can write equations in the form ax plus b. You've already got that down. And of course you could change out different signs of operation there. You could substitute in numbers instead of the letters and have 3x minus 4 and be able to write it that way and solve it. This week, we're going to add to that the form of writing powers, superscripts, or things like subscripts as well. So what we mean by that in print is a superscript is something that instead of being written right at the same level as your baseline, is written up above, like in x cubed. That would be a superscript. Something that is a subscript might be written below the baseline, so it might be x sub 3, and that's how we'd read that. You see this sometimes in math to separate x sub 3 from its other versions like x sub 2 and x sub 1. You also see this a lot in chemistry with things like H2O, that the 2 would be written down below. So that's pretty common. So how do we do these things in the Nemeth code? If we take x squared, which is a nice common example that you might need to write in print. To do that, the 2 is written a little bit smaller and it's also written above the baseline. In Braille, though, we can't just move the 2 up above the baseline. It might look like a B, or it might look like it's on a different line of the text. So everything in Braille is written linearly. How do we deal with the squared then, that x squared? We use a special symbol, the .45, to tell us that the next thing that's coming is up high. So .45 tells us to raise up into the superscript and read whatever comes after as being part of the superscript. And it continues to be in effect until a space or the end of the term or a couple of other special cases for how to end it. So in general, if we want to do x to the power of 2, it would look like this. The to the power of is a sign of operation. It tells us that we're squaring something or we're multiplying it to itself the number of times in the power. And because it's an operation, in Nemeth, it's treated like an operation, and that means it sets numeric mode. So when we do our squared, we don't need to also have a numeric indicator in there. There's no need to put that numeric indicator in. It saves us some space because the operation already sets numeric mode, and that means we can just have our 2 right after it. So if we wanted to write x squared, it would be x to the power of 2 is how we'd write it. And the print would be x to the power of 2. So this to the power of indicator, this superscript indicator, does not have its own written form in print. It just tells us that this is written a little bit smaller and up high. Because that .45 is treated like a sign of operation in the Nemeth code, it not only sets numeric mode, but that also tells us that there cannot be spaces around it. So I can't put a space between the x and the squared either. I need to keep it unspaced like all other signs of operation. Another feature of that being a sign of operation is that it's acting on whatever's in front of it, that x. So it makes sure that our x is not considered standing alone. That keeps us from needing a grade 1 indicator or an English language indicator in front of the x. Because the x isn't standing alone, we can't confuse this for it squared. It has to be x squared. Then there's no confusion, so there's no need for the English language indicator. We can just get rid of that. The exception would be if this x was not a variable like x, but was something like meters. If it were 15 meters squared, the single letter abbreviation for meters requires an English letter indicator when it's squared, so that it's read as meters squared and not as 15m squared with like an algebraic variable in there. Now let's switch to SimBraille and look at some further examples of how to build equations with superscripts and subscripts. As sort of an aside here, one of the shapes in Nemeth that apparently Duxbury does not want to show in the translation line, is the hollow dot. The 4, 6, and then 1, 6 is just an empty dot shape. It's used for making all sorts of math symbols in advanced calculus. Following our logic of superscripts being written a little bit smaller and a little bit higher, if in Nemeth you needed to write something like, today it's 24 degrees out, we actually make the degree symbol in Nemeth in the very literal way. It's a superscript of a hollow dot. And usually we talk about these 3 cells together just mean the degrees symbol, and they do, but they mean the degree symbol because it is a superscript of a hollow dot. So it's composed of those 2 things. So if you were going to write a temperature, it'd be written like that. If you were going to specify that this is Fahrenheit, then you would do so using the English letter indicator and the capital indicator, since this is F, the Fahrenheit, not F, a variable, and not F, a word. And notice that to do any of that, I am in Nemeth mode to begin with, which is important for writing any of our Nemeth equations. So 24 degrees out today in Michigan, just a little below freezing, nice warm day. In general, anytime you've got a superscript, it will come back down when there's a space. That is the default, and it works every time. If there's a space, your superscript will end. It's also possible to end a superscript other ways. So if you are solving for x squared, and then there's a comma and a space after that, we don't interpret it as it comes down at the space. When it's a comma and a space, we assume that the comma went with it, and so the comma is assumed to be down. And a comma followed by a space will always terminate it. Why do I say followed by a space? Because if you had x to the power of 1,000 and you wanted to put that comma in the 1,000, that would say x to the power of 1,000. It wouldn't say x to the power of 1, comma 000 down on baseline. So that whole number would go up. So the comma has to be followed by a space, but if you have a comma and a space, that will terminate terminate your superscript. The punctuation indicator also terminates superscript. So if a sentence says, solve for, and then you start Nemeth mode there, which I guess means I must have ended Nemeth mode before I got there. Solve for x cubed. Well then, normally I would end Nemeth mode. Bad example. Then I would end Nemeth and have a period. If, however, I was writing that whole equation in Nemeth and was going to keep going in Nemeth after that, but there was a period after the solve for, I could have a punctuation indicator and a period. The punctuation indicator would terminate the superscript mode. With the advent of the Nemeth switch indicators, I'm not sure how often you'll see that in practice, but if there's a punctuation mark directly after a superscript, the punctuation indicator terminates the superscript. So there are the nitpicky technical ways other than a space that you would generally need to know ends superscript. But then let's talk about the real one, which is how do you end a superscript on purpose in the middle of an equation? Because that comes up a lot. Like say I want to write x squared plus 4. Makes sense. If I just write x squared plus 4 though, I have x to the power of 2 plus 4. That is x to the power of 6. X to the power of 6 is not the same as x to the power of 2 and then plus a 4 on the baseline. That would look like x to the power of 2, and then I've got to come back down somehow before my plus sign if I want it to be x squared plus 4. X squared plus 4 is a little easier to solve, so that's definitely what I mean to say. The way we get back down to baseline in the middle of an equation is a .5, the multipurpose indicator. In this case, it means baseline. Then I could write my +4 afterwards. And unfortunately, the Nemeth transcription line that Duxbury is giving us is not very precise. Okay, so I turned on view codes, which I'm not especially interested in these codes up here in the Braille, but I did want to show the codes down in the transcription line at the bottom, because that very literally shows how a Braille reader would read this. So if you look at the bottom, it's showing x to the power of 2 plus 4 power end. So that's telling me all of the 2 plus 4 is up in the superscript, as compared to x to the power of 2 power end plus 4. You're going to see this kind of start-end pattern again in the context of fractions. In Nemeth, it's a normal way for Braille readers to think about what belongs where. So note that the .5 moves that power end from being at the very end of the equation where the space is up to right after the squared, which is where we want it. So is that a big difference whether or not we have this little .5 there? I had a high schooler once ask me why he needed the .5. When he knew that obviously he just meant square. And he was just getting to the point where equations had equations in the superscript. And so we got to talk about it. In this example, the first equation, the x to the power of 2 plus 4 altogether, which you would solve the power first and then take x to that power. So x to the power of 6 versus x to the power of 2 and then adding a 4. If I evaluate that for any number, the bigger the number, the bigger the difference is going to be between the equations. The smaller the number, the smaller the difference would be. So if I evaluate that for the number 1, 1 to the power of 6 is 1. 1 squared plus 4 is 5. So when x equals 1, the difference there is 4. If I make that number just a little bit bigger, let's take and make x 3. X squared, if it's 3, 3 squared is 9, 9 plus 4 is 13. So the equation that I meant to write and need the .5 for would equal 13. Oops. I'm going to go actually set that up for comparison's sake. So I will show that it equals 13 so that I can keep track. Now if I take 3 to the power of 2 plus 4, 3 to the power of 6, and I work that out, then it equals quite a bit more. It equals 729. 729 versus 13. And I've only gone as high as 3. The bigger the number, the bigger that difference is going to be. And that is just an example of why clarity in Nemeth is so important. Missing one little dot could easily change your answer by several hundred. If you're thinking of the role of a TBI and you're preparing materials for students, if you're off by a dot, that could mean the student's answer, even if they did the work right, would be hundreds off from what the teacher was expecting, and could make it look like the student really doesn't understand math at all, even if they do. It's why it's so important to be really precise when we're transcribing math for our students. So the multipurpose indicator will always bring us back down to baseline in a problem like this. Another thing that kind of resets our level is just changing level. You might have an equation that has multiple levels in it. X to the power of y to the power of 2, right? So you could imagine an x up to the y, up to the little 2 above that. How do we do that in Nemeth? We don't just stack them and do x to the power of y to the power of 2, because then it could be a little unclear as to what was the powers of what. So we actually double it up the second time. X to the power of y, that to the power of y means y written as a superscript. And then if the y is squared, we're going to do to the power of 2, or the .45.452, and that tells us the 2 is written at the second level above baseline. So it's up that second level higher. And that would be how you'd write that. So you can take things to multiple powers, but they don't add on top of each other. You actually specify how many lines up you're going. Sometimes you get things to powers with subscripts as well. And they are formed the same way. Like if it was x to the power of y sub 1, then I would do the subscript superscript 1, and that prefix right there would let me know that I'm in the subscript of the superscript rather than the other way around. So you can stack all of those together to get pretty much anything you want. Time for a quick commercial break while we're talking about stacking powers and the impact that has. Today's class was brought to you by the number 9 to the 9 to the 9th, which is a number that is 78 digits long if you'd like to work that out. It's no joke when it says solve that on a computer. Now back to our regularly scheduled programming. Subscripts are written with dots 5, 6. As I just kind of previewed right here, it looks just like the superscript indicator, but instead of being at the top, it's at the bottom, so it'll be a little bit lower. We use these a lot in series notation, so x sub 1, and then there might be a comma, x sub 2, and I'm writing this out more diligently than we normally would, x sub 3, just as an example of how that might look. But we actually have an even shorter hand for that when it's just numbers. When it's just a number following a letter, we don't use the subscript indicator at all. Because in math, you never have a number following a letter. Just a letter with a number after it. That doesn't happen. The number after it is always a subscript, so we just assume that. This is true whether you're talking about letters like variables in math or talking about letters like a chemical in chemistry. You even can see that Duxbury right now recognizes that there's a subscript end after that 3 because it's recognizing that shorthand. If I want to write water, I can just write H2O, and that is actually read as the subscript where the 2 is down below. When we assume a subscript, it only works if you have a letter followed by a number. The number has to be just a plain number, and it only applies to that number. Like in H2O, I don't need to do anything to come back to the baseline. If instead I wanted to write something more complicated than a number in the subscript of my variable, then I would need the go down to the subscript indicator, that dot 5, 6. Then I could do x sub y, I could do x sub j, I could do x sub k, and have a list of x's with subscripts. If I wanted to write an equation with those terms, then I could add x sub y, and if I wanted to add it to x sub j, before I can add them together, I need to come back up to the baseline, because remember that my subscript sends me down into the basement until there's a space, a comma and a space, a punctuation indicator, or a dot 5 multipurpose indicator. So I'll use that dot 5 to come back to baseline, and then I can add my x sub j to it. So here I have x sub y plus x sub j. I don't need a dot 5 at the end because I don't need a dot 5 where there's a space, a comma and a space, a punctuation indicator, or if it's just plain the end of the line, if it's the end of the equation, we don't come back to baseline for nothing. We only come back to baseline if we need to because Nemeth is all about saving space. Those are sort of my highlights for you this week as you work your way through the chapter on superscripts and subscripts. They work pretty well in Nemeth. They're easy to read and easy to understand once you're familiar with them. So if that concept of superscripts and subscripts is still throwing you off a little bit, I'd encourage you to play around with writing them just in Microsoft Word. Try writing out letters and superscripts using the font option superscript and subscript. You can get to those with the keyboard shortcut Control equals or Control Shift plus. or you can get to it from your home menu next to where you would change font size and alignment. It'll be like an X squared or an X with a little 2 under it. We'll move it. Microsoft Word handles changing things to superscripts and subscripts very similarly to how Nemeth does, and can give you a little more sense of how you need to go into the superscript before you start writing there, and then how you have to actively come out of it to make it stop. So it's another way you can play with the concept behind the Braille in a visual way outside of the Braille if you find that helpful. Either way, read your book closely this week, and I'll see you all back next week. Until then, happy Brailing!